All right, and welcome to another day of math. Well, we are going to be doing a topic that is actually not too hard in this video. It's back to fundamentals of calculus for a little bit. We will resume the differential equations topic once we get a few more tools in the toolkit. And the first of those tools is going to be partial derivatives. But before we begin, I need to have a quick rant, by which I mean this is something that triggers me. Is it important? Absolutely not. But I'm going to put it out there. So when you write a partial derivative, df/dx, there are people out there, and those people are wrong, who will say that these are deltas. They are not deltas. I have written the letter delta right here. And by written, I mean typed. That's a delta. That's a curly D. Notice that they're not the same thing. This actually does matter a little bit in certain specific contexts, and we will get back to that at the very end of the video, actually. But you can just say df/dx. If you need to be very precise, which of course you may, then you can say partial f partial x. But it is not delta f delta x. That's a different thing. Okay, great. My rant is out of the way. So partial derivatives. The thing is that we have functions of multiple variables in the world. Things don't only depend on x. Things depend on positions and momentums and energies and concentrations and pHs and like who knows, all kinds of stuff out there. Electric fields, whatever. So when we have these multivariable functions, we need to talk about rates of change with respect to different variables to say, okay, I want to know how much my function f changes if one variable changes while the others are unchanged. This is the purpose of the partial derivative. So in order to calculate a partial derivative, the recipe is pretty straightforward. Step 1, write down your stuff. Step 2, think about which variable you are differentiating with respect to. Then take the derivative, and this is the step that actually requires the being careful, the bookkeeping, is that when you're taking a partial derivative with respect to one variable, all of the others are treated as constants while you are taking this derivative, even though they actually are variables with unknown, potentially changing values. For this step, we're going to say, okay, but while those things remain fixed, I'm going to let one variable only change. And so you take your derivative and then you write down your answer and you're done. Great, hooray, let me show you one. We'll start simple. Here's a nice two variable function. So if I take the x partial derivative of this, df/dx, then I take the x derivative of both of these terms. And because this is an x partial derivative, well, ddx of x squared will just be 2x, no big deal. ddx of y squared is 0, because for the sake of this calculation, we're treating y as a constant. The derivative of a constant is 0. And so our partial derivative of the function with respect to x is just 2x. Now, there are other ways to write these things that are a little bit condensed. Some people are really into this, some aren't. You will see this notation. I'll use it occasionally to help people get a little more comfortable with it. Whether you use it yourself or not is totally up to you. But you'll see this notation, dx of f, d sub x of f, and this just means df/dx. So it saves you writing a letter and a fraction bar. 2 letters in a fraction bar? No, it saves you 1 letter in a fraction bar. I had to think about that. It's amazing how you can like teach really advanced math and not know how to count. Okay, but this is only notation. It's just shorthand. There is no difference whatsoever in meaning. But when you see this, there you go. So save a letter or don't. I don't really have any strong feelings about it. Okay, I want to show a little bit more complicated example because you can't forget all of your other calculus rules, chain rule, product rule, like all of that business is still very much in play. So here's our function. We're going to take the x partial derivative of this. So when we're taking the x derivative, y is constant, z is constant. That means 1 over z is just a constant coefficient, and so you pull that out front. Then we have to do chain rule because we have a function of x, because it's log of x cubed with y stuff in there. So we take the derivative of log, and we get x cubed 1 over x cubed y squared. That's from, derivative of log of something is 1 over the thing. But then we also have to take the x derivative of the inside because chain rule, and so you get 3x squared y squared. The y squared is still hanging out there because it's still just a constant in this calculation. So the y's cancel, we get 3 over zx or zx. But there is a second way to do this. You can save yourself a little bit of pain by remembering properties of logarithms. And I'm just going to fix that little typo there. Sorry about that. So you can still factor out the 1 over z, and then you can say, oh yes, log of a product is the sum of the logs. So I have log of x cubed plus log of y squared. And this does save you doing the chain rule business a little bit. You still have to do chain rule with log of x cubed, but you don't have to worry about the y coefficient and what to do with it and where to keep it and where to cancel it, because now you just have log of a constant. And so the derivative of that is 0 and it just disappears entirely. And you get the same answer in the end, which you have to get the same answer in the end because we've just rearranged the problem. So you can use either method. Great, there's partial derivatives. Ta-da, done. You do some practice and you're like, okay, I remember how this works. So what if we have to take multiple derivatives, multiple partial derivatives? If you are doing multiple derivatives with respect to the same variable, you just stack them up the same way you do in single variable calculus. However, once you involve derivatives of multiple different variables, you do have to be careful about a few rules. Because in principle, the order of differentiation could matter. If you are thinking about a function that's in a plane, right? So we've got our xy plane here. Thinking about this geometrically, df dx is a little step this way, and then df dy is a little step that way. But then if you did them in the other order, if you did df dy first, and then df dx first, those paths are very slightly different. So if you are thinking about vector functions, for example, if you are thinking about functions where, oh, big spoiler for next time, if the integral of the function on a closed loop is not 0, if it's not a conservative function, Math 215 comes flooding back into everyone's memory. Or don't. Maybe you blocked it out. I don't know. But there are cases where the order of differentiation can matter. Now, having said that, in the physical world, most functions that we use to describe our universe are well-behaved functions because we believe that the universe is well-behaved for the most part. We think that things are continuous, we think that things are differentiable. And so for well-behaved functions, for functions with just basic properties that seem kind of common sense if we're using them to model the actual world, you can do the derivatives in either order. It's fine. But there are problems where the order does matter. So it's better to just have good habits and always follow the order as it's written, and then you'll never get into trouble. Okay, so how do you follow the order as it's written? This is where you just need to write out what you mean to see how it happens. This is the x derivative of the y derivative of f as it's written. So that means that you take the y derivative first, and then the x derivative will act on that. So that's what this notation means. And if you wanted it to be in the other order, then you would write d squared f dy dx. And that would mean that the x derivative is closest to the f, so you take the x derivative first and then take the y derivative. Great. So that's that. That's order of operations. It's not a big deal. It's just something to keep in mind. And if you're like, I've seen something else where order of operations matters. Yes, you sure have. Because matrix multiplication is not commutative. Order of multiplication does, in general, matter for matrices. And so when we were doing this kind of matrix multiplication, acting on vectors, transforming vectors business, like when we did compound rotations way back weeks ago, we had to do things in the order that they were written. And so this is very analogous to that stuff that we were looking at before. Is it just a coincidence or is it something more? Wow, I don't think I'll answer that question right now. Let's show that we can work these things out. So we'll have a second derivative here, this cross partial derivative, dx dz. And again, order of operations, the z is closest to the f, so we take the z derivative first. Z derivative of 2z e to the xy is 2e to the xy. And then we take the x derivative of that, derivative of an exponential, we get the exponential back, but we do get this y coefficient, because again, that's a constant under this derivative, comes out front because of chain rule. Or if you wanted to be really fancy about it, you could say, ah, yes, I know the exponential is an eigenfunction of the derivative operator, and so I get out y as the eigenvalue under this. If you're down with that, great. If you're not, it's okay. We'll get there. But I take so much joy in this stuff that I can't help it. You know what I also get joy from? Thermodynamics. Now, I know like the torches and pitchforks are coming out here, but bear with me. It's going to be okay. Here's the thing about thermo. First time I took I can't even talk anymore. First time I took thermo, I didn't understand it. Second time I took thermo, I really didn't understand it. Third time I took thermo, I was like, I think I see what's happening here. And then the fourth time, I was like, this is great. I love this stuff. So I don't know, maybe it's Stockholm syndrome. Maybe it's just a matter of getting good. But thermo actually can really be a wonderful subject if you invest enough suffering to get to the point where you really get it. So the biggest application of partial derivatives that's very direct and obvious and easy to point to in material science is these thermodynamic state functions, the Maxwell relations, the relationships, interrelationships between temperature and volume and entropy and pressure and all these different energies. This is where partial derivatives really shine, because knowing how to take derivatives of our different state variables let you calculate all the different thermodynamic properties of your system. If you're like, okay, I know my pressure function, I need to find out what my free energy, like my Gibbs free energy is. Okay, great. We have relationships that will help you work this out. And it really is a very practical thing to be able to apply to understand how systems change, how material systems change in their properties, which phases become stable and unstable, for example, as their free energy changes based on pressure, temperature, environmental variables. Because that's what heat treatment is. That's how we change microstructure, is by heating systems so that the relative energetic favorability of different phases changes, and so we form or unform different phases in the material to change its overall properties. All right, great. Well, that was my rant about partial derivatives. We're at 15 minutes. That's good enough. I don't want to overstay my welcome here. The next video will be looking at vector derivatives, and that is going to take a little bit more. So that's it for now. I'll see you in the next one.